either factoring or using the quadratic formula. In some examples, factoring doesn't work. It's not possible to factor the equation. But in fact, using the quadratic formula will always work, even if it's also possible to solve it by factoring. So you can't really lose by using the quadratic formula. It's just sometimes it'll be faster to factor instead. This video is about solving rational equations. A rational equation, like this one, is an equation that has rational expressions in it. In other words, an equation that has some variables in the denominator. There are several different approaches for solving a rational equation, but they all start by finding the least common denominator. In this example, the denominators are x plus 3 and x. We can think of 1 as just having a denominator of 1. Since the denominators don't have any factors in common, I can find the least common denominator just by multiplying them together. My next step is going to be clearing the denominator. By this, I mean that I multiply both sides of my equation by this least common denominator, x plus 3 times x. So I multiply it on the left side of the equation, and I multiply by the same thing on the right side of the equation. Since I'm doing the same thing to both sides of the equation, I don't change the value of the equation. Multiplying the least common denominator on both sides of the equation is equivalent to multiplying it by all three terms in the equation. I can see this when I multiply out. I'll rewrite the left side the same as before pretty much, and then I'll distribute the right side to get x plus 3 times x times 1 plus x plus 3 times x times 1 over x. So I've actually multiplied the least common denominator by all three terms of my equation. Now I can have a blast canceling things. The x plus 3 cancels with the x plus 3 on the denominator. Here nothing cancels out because there's no denominator, and here the x in the numerator cancels with the x in the denominator. So I can rewrite my expression as x squared equals x plus 3 times x times 1 plus x plus 3. Now I'm going to simplify. So I'll leave the x squared alone. On this side I'll distribute out x squared plus 3x plus x plus 3. Hey, look, the x squareds cancel on both sides, and so I get 0 equals 4x plus 3. So 4x is negative 3 and x is negative 3/4. Finally, I'm going to plug in my answer to check. This is a good idea for any kind of equation, but it's especially important for a rational equation because occasionally for rational equations you'll get what's called extraneous solutions, solutions that don't actually work in your original equation because they make the denominator 0. Now in this example, I don't think we're going to get any extraneous equations because negative 3/4 is not going to make any of these denominators 0. So it should work out fine when I plug in. If I plug in, I get this. I can simplify the denominator here. Negative 3/4 plus 3. 3 is 12/4, so that becomes 9/4. And this is 1. I'll flip and multiply to get minus 4/3. So here I can simplify my complex fraction. It ends up being negative 3/9, and 1 minus 4/3 is negative 1/3, so that all seems to check out. And so my final answer is x equals negative 3/4. This next example looks a little trickier, and it is, but the same approach will work. First, I'll find the least common denominator. So here, my denominators are c minus 5, c plus 1, and c squared minus 4c minus 5. I'm going to factor that as c minus 5 times c plus 1. Now, my least common denominator needs to have just enough factors that each of these denominators divide into it. So I need the factor c minus 5, I need the factor c plus 1, and now I've already got all the factors I need for this denominator. So here is my least common denominator. Next step is to clear the denominators. So I do this by multiplying both sides of the equation by my least common denominator. In fact, I can just multiply each of the three terms by this least common denominator. I went ahead and wrote my third denominator in factored form to make it easier to see what cancels. Now, canceling time. That dies. This dies. And both of those factors die. Canceling out the denominator is the whole point of multiplying by the least common denominator. You're multiplying by something that's big enough to kill every single denominator, so you don't have to deal with denominators anymore. Now I'm going to simplify by multiplying out. So I get, let's see, c plus 1 times 4c, that's 4c squared plus 4c. Now I get minus, just c minus 5. And then over here I get 3c squared plus 3. I can rewrite the minus quantity c minus 5 as minus c plus 5. And now I can subtract the 3c squared from both sides to get just a c squared over here. And the 4c minus c, that becomes a 3c. And finally, I can subtract the 3 from both sides to get c squared plus 3c plus 2 equals 0. I've got myself a quadratic equation. It looks like a nice one that factors. So this factors to c plus 1 times c plus 2 equals 0. So either c plus 1 is 0 or c plus 2 is 0. So c equals -1 or c equals -2. Now let's see, we need to still check our answers. Without even going to the trouble of calculating anything, I can see that c equals -1 is not going to work. Because if I plug it in to this denominator here, I get a denominator 0, which doesn't make sense. So c equals -1 is an extraneous solution. It doesn't actually satisfy my original equation. And so I can just cross it right out. C equals -2. I can go, if I go ahead and that doesn't make any of my denominators 0, so if I haven't made any mistakes, it should satisfy my original equation. But I'll just plug it in to be sure. And after some simplifying, I get a true statement. So my final answer is C equals -2. In this video, we solved a couple of rational equations using the method of finding the least common denominator and then clearing the denominator. We cleared the denominator by multiplying both sides of the equation by the least common denominator, or equivalently, multiplying each of the terms by that denominator. There's another equivalent method that some people prefer. It still starts out the same. We find the least common denominator, but then we write all the fractions over that least common denominator. So in this example, we'd still use the least common denominator of x plus 3 times x, but our next step would be to write each of these rational expressions over that common denominator by multiplying the top and the bottom by the appropriate things. So 1, in order to get the common denominator of x plus 3x, I need to multiply the top and the bottom by x plus 3 times x. 1 over x, I need to multiply the top and the bottom just by x plus 3, since that's what's missing from the denominator x. Now if I simplify a little bit, let's see, this is x squared over that common denominator, and here I have just x plus 3 times x over that denominator, and here I have x plus 3 over that common denominator. Now I'll add together my fractions on the right side, so they have a common denominator. So this is x plus 3 times x plus 3. And now I have two fractions that are equal, that have the same denominator, therefore their numerators have to be equal also. So the next step is to set the numerators equal. So I get x squared is x plus 3 times x plus x plus 3. And if you look back at the previous way we solved this equation, you'll recognize this equation. And so from here on, we just continue as before. When choosing between these two methods, I personally tend to prefer the clear the denominators method because it's a little bit less writing. You get rid of those denominators earlier. You don't have to write them as many times. But some people find this one a little bit easier to remember, a little easier to understand. Either of these methods is fine. One last caution, don't forget at the end to check your solutions and eliminate any extraneous solutions. These will be solutions that make the denominators of your original equations go to 0. This video is about solving radical equations, that is, equations like this one that have square root signs in them, or cube roots, or any other kind of radical. When I see an equation with a square root in it, I really want to get rid of the square root. But it'll be easiest to get rid of the square root if I first isolate the square root. In other words, I want to get the term with the square root in it on one side of the equation by itself and everything else on the other side of the equation. If I start with my original equation, x plus the square root of x equals 12, and I subtract x from both sides, then that does isolate the square root term on the left side with everything else on the right. Once I've isolated the term with the square root, I'm going to get rid of the square root. And I'll do that by squaring both sides of my equation. So I'll take the square root of x equals 12 minus x and square both sides. Now the square root of x squared is just x. Taking the square root and then squaring, those operations undo each other. To work out 12 minus x squared, I'll write it out and distribute. 12 times 12 is 144. 12 times minus x is minus 12x. I get another minus 12x from here. And finally, minus x times minus x is positive x squared. So I can combine my minus 12x's, that's minus 24x. And now I can subtract x from both sides to get 0 equals 144 minus 25x plus x squared. That's a quadratic equation. I'll rewrite it in a little bit more standard form here. So now I've got a familiar quadratic equation with no radical signs left in my equation. I'll just proceed to solve it like I usually do for a quadratic. I'll try to factor it. So I'm going to look for two numbers that multiply to 144 and add to minus 25. Well, I know I'm going to need negative numbers to get to negative 25, and in fact I'll need two negative numbers so they still multiply to a positive number. So I'll start listing some factors of 144. I could have negative 1 and a negative 144, negative 2 and negative 72, negative 4, negative 36, and so on. Once I've listed out the possible factors, it's not hard to find the two that add to negative 25, so that's negative 9 and negative 16. So now I can factor my quadratic equation as x minus 9 times x minus 16 equals 0. That means that x minus 9 is 0 or x minus 16 is 0, so x equals 9 or x equals 16. I'm almost done, but there's one last very important step, and that's to check the solutions so that we can eliminate any extraneous solutions. An extraneous solution is a solution that we get that does not actually satisfy our original equation, and extraneous solutions can happen when you're solving equations with radicals in them. So let's first check x equals 9. If we plug in to our original equation, we get 9 plus the square root of 9, and we want that to equal 12. Well, the square root of 9 is 3, and 9 plus 3 does indeed equal 12, so that solution checks out. Now let's try x equals 16. Plugging in, we get 16 plus the square root of 16, and that's supposed to equal 12. Well, that says 16 plus 4 is supposed to equal 12, but that most definitely is not true. And so x equals 16 turns out to be an extraneous solution, and our only solution is x equals 9.